Walking around these ruins of Segóbriga, one cannot help but wonder, what sense does this splendid Roman city make in the middle of a deserted, lonely stretch of land? Where did Rome get the wealth to build it? What was the occupation of those who filled this amphitheater and made the circus roar? Cristallus. This stone is cleaved and stripped into sheets as thin as desired. In ancient times, it was found in Hispania Superior, and not in the entire province, but only in the area within 100,000 steps around the city of Segóbriga. These words were written by the Roman historian Pliny the Elder in volume 36 of his Natural History, the most complete encyclopedia of the Roman world. Now we know that Segóbriga's prosperity revolved around mining, and the mineral that created this isolated emporium was selenite. Giant gypsum crystals, the Lapis specularis, the so-called crystal of Hispania. The mystery of the giant crystals. The lapis specularis mentioned by Pliny is nothing else than pure gypsum in crystallized form. Large gypsum crystals extracted from a strip of land measuring 100,000 Roman steps, or about 90 miles. That stretches from north to south around Segóbriga, located between what we know today as the Alcarria and La Mancha in central Spain. In Roman times, crystals were a very highly prized commodity. In the sophisticated Rome, the only way to close window openings in palaces and high-class houses, to separate areas within buildings, or to build greenhouses to cultivate fruits and vegetables, was use of these natural translucent rocks. But among them all stands out one in particular, the crystal. Ancient Greeks called these transparent stones kristallos. They thought crystals were supercooled water, krios, which ultimately gives its origin to the word kristallos. I invite you to travel with me in search of the largest crystals known in the world, a journey to the sheer beauty of the mineral world. From these hills where the glitter of the sun heralds the promise of the treasures beneath, expert miners extracted the largest and most transparent crystals the world has ever seen. Crystals that could reach up to 7 feet long. They were the cristallos of Hispania. After the extraction, the Romans took advantage of a remarkable property of these crystals, the cleavage, to obtain slabs, which were later sawed to produce the different sizes that were standardized at that time. Departing caravans from Segóbriga transported the valuable crystals to the ports of Sagunto or Cartago Nova, known today as Cartagena in eastern Spain. Then the crystals were shipped to the opulent Roman metropolis, and from Rome to the rest of the empire. But at the end of the 1st century, the Romans gained the technology to produce flat glass, a find that became a death sentence for Segóbriga. Even though the glass plates produced by Rome were not as ornate or transparent, they were considerably cheaper. These glass slates would mean the end of Segóbriga as a prosperous town. And these new transparent slates would eventually take the word crystallos to name a cheap and transparent material that was nothing other than synthetic glass. This is the origin of the confusion between two words with very different meanings. The difference between crystal and glass, between a diamond and amorphous carbon, between the green emerald and common costume jewelry, is none other than order. In the structure of a glass, the atoms are disposed without any pattern, just like the soldiers of a dispersed army. In a crystal, however, atoms are deployed in perfect order, just like the soldiers of a battalion in rigid formation. This order is what gives crystals the inherent beauty of their linear forms, so different from the curves in life. Their constant and perfect angles, their luster and color. These forms based in that mineral order have fascinated mankind since the beginning of time. The Romans did not distinguish quartz or rock crystal from gypsum. Any transparent faceted mineral was considered crystallos. Today we know that gypsum crystals are composed of calcium sulfate molecules stacked in layers, alternating with other layers of water molecules. These layers of water molecules are less tightly bound in the structure of the crystal. This is the reason why, when a gypsum crystal is stricken or cleaved, the structure breaks in favor of those layers. It is exfoliated. This property, which fascinated Pliny in his chronicle, was used by Roman miners to cleavage the crystals into thin slices. Other crystals are formed by other molecules ordered in such a way that gives them other fascinating properties that we use in our daily lives. For example, our skeletons and teeth are made of calcium phosphate. Many cosmetics are composed of tiny crystals, whose shape and size determine their color and quality. That bicycle has its frame made of light crystalline alloys, and all modern electronics is based on crystals. At the dining table, salt and sugar are clear examples, but also the quality of chocolate depends on the crystals of its fatty acids, while the texture of ice cream will depend on the nature of the ice crystals used in its fabrication. Eggshells are made of crystallized calcium carbonate, as well as seashells, coral and pearls. The vast majority of pharmaceutical drugs are crystalline products, and in order to understand how life works at molecular level, we need to obtain crystals of proteins and nucleic acids. But in my entire life as a crystallographer, I had never found crystals as large as these from Segóbriga. Pliny was right. They had no parallel in the entire Roman world. But after the gypsum mines were closed, the previously prosperous and lively city ended up in ruins. Its homes and public buildings were abandoned, and the memory of its splendid mines lost in time. So much so that until recently, when archaeologists Juan Carlos Guisado and María José Bernardez rescued them from oblivion, nobody had heard about those mines that contained the most spectacular sample of the mineral world known until then. Until then. Because I would never have imagined that Mother Nature was holding another remarkable sample of giant gypsum crystals located just 500 kilometers south of Segovia, in the Betic mountain range. We are now in Pulpi, near Almería, in southern Spain. Here in the eastern flank of the Aguillon range, we can still see the remains of mining facilities that were operated from the middle of the 19th century until well into the 20th century. This mountain has been drilled with numerous mining galleries, such as this one we are now walking through, called Quintal Pensada, or Who Would Have Thought, also known as La Mina Rica, or the Rich Mine. Here within these tunnels and chimneys, excavating these walls and sliding through these narrow passages, miners ripped minerals such as lead and iron. Surely they would sometimes find beautiful gypsum crystals, which eventually they would offer to their patrons or sell to collectors. But by a few inches, they missed the most beautiful treasure hidden in the Mina Rica. Amateur mineralogists digging in abandoned mines in search of samples for their private collections would hit the jackpot 50 years later. Here, behind a small and inconspicuous cavity, just like many others in the rock, lay hidden the great geode of Pulpi.
Wow, espectacular.
This geode is an egg-shaped cavity measuring 25 feet long, 7 feet wide, and about 5 feet tall, and its walls are covered by enormous gypsum crystals of a near-perfect transparency. In a place like the geode of Pulpi, one cannot help but to recall the original meaning of the word crystal: supercooled water. In fact, the sheer transparency of the crystals covering this geode makes them look like large blocks of ice. In some of the pulpi crystals, we can still see small impurities made of iron and manganese, which are markers of their growth stages. Because all crystals grow as their composing molecules slowly stick to the surface of them. The glue in this process is the chemical bond that links the molecules in the crystal. It's somewhat like playing Tetris. Just like in the game, the slower the molecules adhere to the arranged surface of the crystal, the better will be the quality of the arrangement, and therefore the quality of the crystal itself. In order to prove this process through an experiment, we went to the Science Park of Granada in Spain. Here we will perform a simple test with the help of some students who won a high school crystallization contest. We will heat two identical dissolutions of a specific salt and let them cool down in order to form crystals. One of them will be locked into a styrofoam container in order to let it cool down slowly, while the other will cool down faster out in the open. The results are evident. The dissolution that cooled down slowly formed fewer crystals, but these crystals were significantly larger than those created by the fast-cooling dissolution. The big crystals of Segobriga and the geode of Pulpi must have formed very slowly to become the largest gypsum crystals in Europe. But why? When? How? At this point, there was no turning back. I was now captivated by the beauty and the mystery of those crystals, and it became an obsession for me to find out their origin and how they were formed. I went through the literature on the subject in search of a clue. Any information about those crystals or any others of similar size. I found out that on the other side of the Atlantic in North America, the mineral world was holding even more impressive scenarios. Reading an old book, I learned that hidden in the depths of the Mexican desert of Chihuahua, a cave was discovered in 1910, which became famous for its spectacular gypsum crystals. It was dubbed La Cueva de las Espadas, or the Cave of the Swords. It was located in a mining town called Naica, and there I went to study those crystals. We are in the desert of Chihuahua in northern Mexico, the harsh and inhospitable scenario of many Western-style films. In fact, we are traveling through a desert that was home to the Apache tribe in the 19th century. Here we find a mountain called Naica in the language of the Taramaica Indians, which means the mountain that gives shade to the desert. It's a mountain that hides one of the world's largest reserves of lead, silver, and zinc. The mineral was first exploited during the 19th century by gambusinos, self-employed miners who would extract metal-rich minerals almost from the surface. But there was still more mineral beneath the galleries, already flooded by subterranean waters. Industrial, planned, machine-based exploitation began by the end of the 19th century. For more than 60 years, the Naica mine has been continuously exploited. In 1951, Mexico started to control ownership, and since 1998, mining activity is 100% Mexican, controlled by the Peñoles group. We are walking down the San Francisco ramp along with engineer Roberto Villasuso. Roberto is the chief of exploration at Naica, and the man who best knows the geology of this mine. The ramp is a tube-shaped road about 5 meters in diameter, which zigzags downwards to a depth of 2,700 feet, in which today we find the mining front. We stop at a depth of 390 feet, the location of the cavity found in 1910 that I have come to visit. This cavity, currently accessible through a wooden platform pathway, is a corridor about 980 feet long, and its walls are entirely covered by gypsum crystals, watching your every move like menacing swords, each measuring between 1 and 1.5 feet. Everything, floors, walls, ceiling, is crystallized. And it must have been even more so because the abandon and plundering are evident. These crystals were formed when this corridor was totally flooded by waters rich in salts. Some of them have a darker tonality due to the presence of particles of clay and iron oxide. This indicates that the cave was flooded in an intermittent way, with waters closer to the surface and richer in oxygen. In fact, at the depth level of the cave, at about 390 feet, we can find today the level of these subterranean waters. This cave, this corridor of glittering crystal walls, is the Cueva de las Espadas of Naica. If the cristales of Segobriga took me to that phenomenal crystal egg, the geode of Pulpi, this enigmatic and intriguing cave of the swords stirred up my curiosity even further. I kept searching, and I learned that 5,000 miles away from Chihuahua, South America was holding another surprise for me. You would think we are inside a train station, a port, or an industrial town. And you'd be wrong. Although it might be hard to believe, we are inside the largest subterranean mine in the world. In this mine, 1,600 miles of galleries have been excavated, as much as the distance between Paris and Moscow. And every year, around 500,000 tons of fine copper are extracted. We are in El Teniente mine at about 7,000 feet above sea level, located in the western flank of the Andes mountain range. This mineral deposit was formed about 5 million years ago when the Nazca and South American tectonic plates collided to create the stunning Andes mountain range. Hot fluids created these deposits of copper minerals that surround a large volcanic chimney. The Teniente mine has a long history from its initial exploitation in pre-Hispanic times. Today, El Teniente belongs to the Corporación del Cobre, or Copper Corporation, the Chilean company which exploits it since its nationalization by Salvador Allende's government in 1971. Since Rancagua, the closest town to the mine, is located 31 miles away, accessible only through a winding mountain road, at the beginning of the 20th century, a mining settlement was created in one of the hillsides of El Teniente, which in time was denominated Sewell. This settlement would eventually be home to about 15,000 people. The architecture of this mining town is quite singular. Sewell experienced times of extraordinary social activity, but also it experienced what could possibly be the largest tragedy in the history of mining. It happened on June the 19th, 1945. On the afternoon shift of that fateful day, 355 men died poisoned by carbon monoxide fumes, generated by an accidental fire in one of the forges. The tragedy paved the way to significant changes in the safety codes of modern mining. And today, especially in El Teniente, those codes are very strict. After the nationalization of the mine, most inhabitants of Sewell left, but this abandoned town still kept so much charm and singularity that was designated a Universal Heritage Site in 2006. In the well-kept museum exhibiting the town's history, we found some clues about what we were looking for. The largest gypsum crystals known to date. We went down to study them in the caves where they were formed. We are now at level 6 of El Teniente. At this level, several caves with gypsum crystals have been discovered throughout the years. The largest of them is La Caverna de los Cristales, or the Cave of Crystals. It's fascinating. Not surprisingly, this cave is famous worldwide. The walls are covered by golden crystals of pyrite and barite. But the immense gypsum crystals stand out as the real protagonists. They are crystals measuring about 25 feet long, crossing the cavity from side to side. But in addition to recognizing the minerals of the walls, little can be investigated in a place so long exposed to air from the outside, which is frequently visited by tourists from all over the world. Geologists had located 6 different caves in which giant gypsum crystals were found, and invited us to visit one of them, which was closed after being discovered 12 years ago, and which nobody had entered since. The cave was truly closed. To access it, it was not easy. An iron door was sealing the entrance. But inside this modern mine of El Teniente, everything is well organized. With the enthusiastic help of the chief of workshops, we finally managed to enter. Inside, waiting for us, there they were, large crystals no one had touched until now. We were all excited. The researchers who came to study them, the miners who had never entered the cave, and one of the local geologists who took us there, Arturo Morales. The transparency of these crystals is the same or even better than those of pulpi or segobriga. We took measurements in the pertinent samples, among them crystals containing fluid inclusions, which are microscopic bubbles filled with liquid. The same liquid from which the crystals were formed. Like a message in a bottle, those tiny pockets contain essential information about the composition of the mother water, as well as the temperature at which the crystals were formed. We also noticed with amazement that some seismic activity had plastically curved these immense crystal beams. Accustomed to growing crystals in the laboratory, I knew how difficult it would be to create the crystals like those of the Cave of Spades in Naica. Even more difficult would be to explain the formation of those colossal crystals of El Teniente, because they require conditions that would have to be maintained for the longest time, something that rarely occurs in nature. No crystallographer could hope for anything more beautiful or more exceptional. But back in Mexico, engineer Roberto Villasuso had a huge surprise in store for us. We had to return to Naica. Thanks to the first water pumps, freelance Gambusino miners, as well as the first industrial miners at Naica, could excavate galleries below the natural level of subterranean waters. The mine seemed endless to exploit, and Naica miners kept searching for mineral at increasingly deeper levels. But they had to overcome an obstacle which, because of its challenge and its cost, virtually makes Naica a water mine. For mining activity to be performed, it is necessary to constantly drain the site. To do so, Naica's engineers pump more than 23,000 gallons of water per minute in a steamy stream that descends through the hillside to the desert, creating an oasis suitable for agriculture. Even though the ramp of San Francisco descends in zigzag to a depth of more than 2,600 feet, it was not necessary to reach that low. What Roberto wanted to show us was at a depth of 950 feet. In April of 2000, during the drilling works of a gallery, 2 miners found a cavity which seemed to contain some gypsum crystals. Those findings were common in the mine, but this time around it was something different and unique, something never seen before. Behind the hole drilled in the rock by the machine, there was an immense cave. They had the good sense to stop the drilling and alert management, who then decided to preserve this wonder. We arrived at the depth level of 950 feet. Behind a metal door and a corridor about 65 feet long in the middle of an intense heat, the cave could be accessed through the hole made by the drilling machine. Behind the hole, the first sensation was simply overwhelming. I became instantly blind because my glasses got fogged, while a strong blast of heat completely confused me. After a few seconds, I managed to recover, forgot about my glasses, and started to look around. I became instantly mesmerized. Perhaps it was only a hallucination. I was stunned, breathing heavily, almost suffocated by a temperature close to 50 degrees Celsius and humidity close to 100%. I was sweating profusely, and all my clothes were soaked. None of that mattered to me, for I was standing before the most beautiful spectacle of the mineral world. I was inside the cave of the giant crystals of Naica. The first visit was enough to fall in love with the challenge to understand this crystalline formation. It was as if nature would dare anyone who would lay eyes on this crystal cathedral. As a crystallographer, I knew what I had in front of me was not an impossible dream to explain. Difficult, yes, but not impossible. At dusk, when the moon would also challenge the sun in the desert sky, I promised myself to unveil, with the help of Roberto and my other colleagues, how this natural wonder was created, how those giant crystals were formed. We went back to the cave dozens of times on different research trips. We decided not to use any kind of protective or special equipment. We would rather move freely and quickly in order not to harm the crystals or alter the temperature of the cave. Employing all our efforts in studying the rock with all the necessary precautions. Someone would ensure that after 8 minutes in the cave, we would all leave it. We would enter the cave only with our measuring instruments and the sheer will to understand this mystery of nature. We moved around the immense columns rightfully dubbed by miners the beams. Some of these columns soared from the floor of the cave all the way up to the ceiling. At more than 10 meters tall and a meter wide, their weight could easily be over 25 tons. How could they remain in that upright position all this time? The reason is that this cave remained flooded by subterranean waters until 1975, when the 950 feet level in which we are now was drained. Until then, the columns were forming very slowly and remained erected inside this big cave, which was totally submerged in water, even resisting small seismic movements. When the cave was drained, the weight of the inclined columns bent them, and in some cases can be seen how the crystal beam actually gives up to the enormous pressure, which represents a problem for preservation. When you enter this cave, you only have eyes for the immense hyaline crystals. But since I entered for the first time, something called my attention. Unlike the Cave of the Swords, the walls and ceiling of the Cave of the Giant Crystals, about 570 feet deeper, were practically bare, without any crystallization. The walls and ceiling, colored in red by the iron oxide, could be clearly seen, with just some crystals highlighting the cracks in the rocks. I realized that to unveil the mystery of Naica, the important question to answer was not only why the crystals were so big, but why were there so few of them? Naica's geological history begins about 30 million years ago. Back then, the Earth's surface was already covered by green prairies for grazing animals. The temperature of the planet fell so much at one point in time that ever since then the Earth have the two poles permanently frozen. Here in the Mexican Sierra Madre, volcanic activity was very significant. Just below Naica, a hot magma started to flow, and its temperature must have reached about 1,500 degrees. It was not strong enough to come to the surface, but it could push up the rocks to form the Naica mountain range. This magma was also able to inject into the rocks a hot and acid fluid, full of metals which eventually created the minerals exploited now by miners. In time, the magma cooled down, and erosion left the mineral close to the surface of the land. So much that Gambusino miners could find it just by trekking these mountains. We discovered that by the end of this mineralization, when temperatures reached about 400 degrees, a mineral was formed that is crucial to explain the origin of the giant gypsum crystals. That mineral is anhydrite, a blue-like mineral that can be found in the deepest areas of the mine, and which strangely has the same composition as gypsum, calcium sulfate, but it does not have the water molecules. The mountain's temperature kept going down, but the remaining embers left of those and further intrusions still heat the rock, and the waters that flow in the depths of Naica at a temperature of about 130 degrees make the Cave of the Crystals a true sauna, or more exactly, a Turkish bath. We had found a good hypothesis to explain the origin of the crystals. We knew that anhydrite, that blue mineral, dissolves when temperature goes down. Therefore, during millions of years, as the Naica mountain range slowly cooled down, subterranean waters were being enriched with calcium sulfate. And we also knew that as waters cool down, another curious phenomenon takes place. They cannot contain so many molecules of sulfate and calcium, and therefore start to crystallize, but in the form of gypsum, incorporating water molecules and forming the layered structure that is typical in gypsum crystals. It was a nice hypothesis, but we had to prove it. First, we had to prove that the molecules that form the gypsum crystals were the same ones that form the anhydrite crystals. This test was performed by Carlos Ayora from the Jaume Almería Institute in Barcelona, using a sophisticated technique based on stable isotopes. His conclusions were that, without a doubt, the same molecules of the gypsum crystals were previously forming the anhydrite crystals. But we also had to establish at which temperature the crystals grew. How can we find out? By studying the fluid inclusions, those small bubbles in the crystal that trap the brine, the mother liquid that contains the same salts from which the crystals were formed. To find those fluid inclusions in Naica's hell-like atmosphere was not an easy task, but we found them, and they were studied by Àngels Canals from the University of Barcelona. The results of the test were conclusive. The gypsum crystals were formed from similar waters to those currently found in Naica at about 130 degrees temperature. Everything made sense. The giant gypsum crystals were formed after the dissolution of the anhydrite during the slow cooling process of the Naica mountain range. As shown in the student experiment at Granada's Science Park, the slow cooling causes fewer crystals to be formed. That is the reason why there are few crystals here. But there is so much anhydrite in the mountain, still hot, that its dissolution provides a small amount of salt on a permanent basis. This mechanism of continuous feeding is responsible for the enormous size of the crystals. And it also explains why there are so many crystals, but smaller, in the Cave of the Swords, which cool down faster because of the contact with surface waters. In 1975, when the mine was drained down to the level of 950 feet below the surface, the crystals were still growing. And if the cave was still flooded by subterranean waters, those crystals would still be growing now. There are unavoidable questions such as, since when have they been growing? How long did they take to form? The crystals are so pure that we have not been able to measure their age by radiometric methods. But in our laboratory of crystallographic studies of Granada in Spain, we were able to perform an experiment that allows us to answer these questions, thanks to a modern microscope, a confocal microscope with different phase contrast. With this microscope, we can see in great detail how the crystal surface grows. We have collected waters from the Naica mine, and we have placed in position a small gypsum crystal. With patience, we have been able to measure through this microscope the growth velocity of a gypsum crystal in those specific waters at a temperature of 132 degrees. Even with this microscope, we had to wait for days to actually see it grow. The values we have obtained indicate that the gypsum crystals grow at around 60 microns, or the insignificant width of a strand of hair, every century. This is the slowest growth velocity ever measured in a mineral process. At this very slow pace, we could estimate that the crystals of Naica must have begun forming about 500,000 years ago. Like fossils, the Naica crystals are a record, the visible trace of the passage of time. To destroy something so singular and so beautiful, which was formed when our species had not even appeared in North America, would be an enormous mistake. Now that we know their origin, we also know that the probability of finding another geological site as Naica is almost zero. What will be the future of these singular crystals when the minerals are gone and the mine stops to be exploited and drained? the caves will be flooded in a week. When that happens, will we allow the crystal caves to be flooded? If so, will the crystals be extracted first, or will the cave continue to be drained to turn the Naica mine into a natural museum with the largest exhibition of the mineral world? If our explanation of crystal formation is correct, besides the ones already known, inside the Naica mountain range, there must be other large crystal caves still hidden among the maze of galleries in the mine. It's that group of caves what makes Naica a unique location, which has been called the Sistine Chapel of crystallography, and the only place on Earth where Superman would feel right at home. We worry, and rightfully so, about preserving the endangered species of the animal and vegetable world. But the mines of Lapis specularis of Segóbriga, the great geode of Pulpi, the big crystals of El Teniente, or the colossal cave of the crystals of Naica are unique and unrepeatable phenomena, and it is also our obligation to preserve them, just as we preserve the Mayan or Egyptian pyramids or the Great Canyon. As beautiful as they may look in a museum or in a private collection, the giant gypsum crystals are meaningless outside of Naica. What must be preserved are not just the crystals. What we must preserve is Naica, Pulpi, Segóbriga, or El Teniente, as what they truly are, priceless treasures of the mineral world. The Romans of Segóbriga would also call these crystals by the name already used by the Greek scholar Theophrastus in the 4th century BC, selenite, a precious name after the goddess of the moon, Selene, which made reference to the moon-like brightness of the gypsum crystals. If the goddess Selene ever really lived on Earth, her home must have been, without a doubt, this beautiful cavern hidden beneath the desert of Naica.